All right. So we're kind of gonna just pick up where we left off last time. We introduced these batteries, right? What we call these voltaic cell batteries. Today we'll take a look at a few different other type of common batteries, but this is kind of our simplest here. We have our anode where oxidation takes place. That releases our electrons that then travel through our wire to our cathode where our reduction reaction takes place. We learned how we can summarize this battery content into what we call standard cell notation. And then we learned how to talk about these batteries quantitatively. First, what we call standard potential, measuring the voltage of that battery by paying attention to the potential of our two reactions, our two half reactions. All right, and then from there we could calculate our delta G of this reaction using our new equation here that we derived. All right, so we're going to kind of pick up here, noticing that when we calculated this delta G, it was specifically our delta G naught, also our E naught. We called this our standard potential. And so what does this little naught mean here? Standard conditions, exactly, right? So this reaction that we just calculated here, or rather these quantities that we just calculated here, are for standard conditions. All right, standard conditions, that's indicated by our little knot here. Is that 298 Kelvin. We're not going to talk too much about temperature. Let's think about our other condition for standard conditions, though, which is that all solutions have a concentration of 1 molar. All right, we can note that gases also have a pressure of 1 atm, although gases are not terribly important in our discussion of batteries. All right, but we know from our look at a battery here that they take place in an aqueous solution. And so again, that standard potential that we calculated for this battery is only true if my iron ions, my protons, my acid ions, my permanganate ions, and my manganese 2 ions, only if everything in this balanced chemical equation is at 1 molar, all right? And so cool, that's all well and good, but within 0.1 seconds of this reaction taking place, those concentrations are no longer gonna be 1 molar, right? Reactants are gonna get consumed, products are gonna get produced. So this is only really true for a snapshot in time here, what the voltage is of this battery. Everything's not going to remain 1 molar forever, right? So how do we calculate our potential? Calculate that E cell for any conditions. Yeah, exactly, right? So we ran into this problem before in our thermodynamics chapter. And how did we factor in these any conditions? We used that reaction quotient Q. All right, so we're actually going to start in a very similar place. We're going to start first with our relationship that we derived between delta G and our potential of our battery. All right. And then we said, all right, well, we don't know what our E cell is under any conditions, but we did have this relationship from our thermodynamics chapter where our delta G without the naught under any conditions was equal to delta G naught plus RT natural log of Q. All right, and again, that Q was how we plugged in those any conditions. All right, well, let's look here. We have delta G naught in this equation as well as in this equation here, so let's just substitute this in here. All right, we're going to say that this is equal to negative NF E naught cell plus RT natural log of Q. right? And that's because that was our delta G naught, was negative NFE, E naught specifically. And so all we're going to do now is say, all right, well, let's just define an analogous term for regular delta G. This is equal to negative NF regular E cell without the naught. All right, so we just plugged in this equation to our thermodynamics equation here, just both with and without that little naught there. All right, and if we reorganize this equation by dividing each side by negative NF, we arrive at this relationship where our potential of our battery outside standard conditions is equal to that standard potential minus RT over NF natural log of Q. All right, so this is our way of calculating our potential under any conditions. And again, it's that Q that allows us to plug in those any conditions. All right, so let's go ahead and use this equation here. We'll go and we'll grab one of our previous practice problems that we did. This first battery that we looked at was this copper zinc battery. All right, so given these two half reactions here, everybody take a second and let's get our balanced chemical equation. All right, remember I'm going to sum up these two half reactions. I just have to make sure what happens when I sum them up. My electrons cancel out. In this case, I already have 2 on either side, so I'm kind of lucky. This one's pretty easy. It's just zinc plus those copper ions gives me copper plus those zinc ions. All right, cool. Then everybody take a second and build me that reaction quotient Q. All right, Q equals what? What do we do? How do we build Q? What do we remember? Products over reactants, but be careful, what's not going to appear in this expression here? The solids, right? So it's just going to be my product, those zinc ions, over my reactant, those copper ions. All right, and we calculated this E naught cell before, but let's just remind ourselves that this E naught cell equals 1.10 volts. And what would we conclude from that value of our E naught cell, specifically the sign of that potential? That this reaction was spontaneous, right? We proved that as well by looking at that delta G. All right, and so importantly, what this, let's remind ourselves what that means. It means it's spontaneous in that forward direction. This reaction will indeed convert zinc and copper ions into copper and zinc ions. Right? That's what we mean by spontaneous, is that this thing is going to move forward. Okay? So now let's imagine that our reaction's been running for a bit, right? This battery's been set up and now it's been running. So now we've accumulated some zinc ions here, right? And we've decreased our copper ions. What effect do we think that's going to have on the potential of this battery? Is it going to increase or decrease? It'll decrease, right? It'll start becoming less and less favorable of a reaction the more we increase our products and the more we decrease our reactants. So let's try to prove that to ourselves using our equation here. Let us ask, what is the potential when our concentration of zinc ions is equal to 5 molar? And our concentration of copper ions is equal to 0.05 molar. All right, with an excess of that solid zinc and solid copper. So whichever direction this reaction goes, we're not worried about that being our limiting reactant. We can just focus on our solutions here. All right, so now plugging these conditions back in, everybody take a second and give me my value of Q, and then we're going to use our equation. All right, we can make a note. We got these constants in here. That F value was Faraday's constant, 96484.6 coulombs per mole electron, and R equals 8.3144 joules per mole Kelvin. Joules over coulombs. Yep. That's a great question. What temperature would we be using here since we're basing this off of our standard cell here? We are using that standard temperature. You can start to, basically you don't want to mess with too many things at once. So you don't want to change both the conditions and the temperature. All of a sudden this becomes less reliable of a formula. So we're worrying about just changing our conditions here and keeping that standard temperature of that 298 Kelvin. Good question. All right, so first of all, if I plug those concentrations in, I get a value of Q of 100. All right, I'm going to plug that into my equation here. I'm going to multiply by R times T divided by N. What is the value of N in this reaction here? All right, so again, that's why we have to charge balance this equation, is paying specific attention to the number of electrons being transferred. In this case, there are 2 moles of electrons that will be transferred per mole reaction. right, so we punch this all into our calculator. We get about value of 1.04. And what are the units going to be on that value? We're talking about potential. What do we measure potential in? Volts, all right? So let's hope that we're going to get volts here, but let's do our math. First of all, we're subtracting two things from one another. They better have the same units. You can't subtract things that have unlike units. So this term has volts. Let's check out this one here. Over here we have Kelvin that cancels out. We also have mole reaction that cancels out, as well as moles of electrons. So what we're left with over here is joules per coulomb, right? But what was the definition of a volt? A joule per coulomb. So indeed, we do work out to our units of volts over here as well. The beauty of units. All right, so we can see that our potential has indeed decreased because we've accumulated some product and we've decreased our reactant. You'll find it's relatively not sensitive at all to concentrations, but this is a pretty small decrease for just how far outside standard conditions we are. That's why batteries don't only work for 0.1 seconds, right? They still maintain a pretty good potential even as we accumulate product and decrease our reactant. Yeah.
Where does the mole of reactions cancel?
That's what R is joules per mole, that mole per mole Kelvin in that value for R, that's mole reaction. And in our value of N here, that's how many moles of electrons there are in a mole of reaction. Cool. All right, so similar to what we had in our thermodynamics discussion, we have our E naught, which means that we are in standard conditions. Well, how do we tell what our potential of our battery is at anything outside of standard conditions? Now we have a new equation for that, right? Relating the potential of the battery outside of standard conditions to its potential at standard conditions minus this term here containing Q. And again, Q is how we plug in those any conditions. Cool. All right, so we started off by looking at these voltaic cell batteries, and y'all took some convincing that this is indeed a battery because you're like, look, I've seen batteries and this looks nothing like it, right? But the important part is that all batteries have these two chambers, one of which an oxidation reaction is taking place. They're physically separated and they won't actually have any reaction occur unless you give a path for those electrons to travel, and that would be through this wire here where the reduction reaction is taking place. All right, so let's take a look at two other common types of batteries. The first one is probably the thing that comes into mind when you think of a battery, which is what we call a dry cell battery. All right, so this would be, for example, your Duracell AA, AAA, etc. All right, and if we were to slice this thing open here, we would see these four main parts to this battery. The first is this rod that sits in the middle, which is made out of carbon, or more specifically graphite, which is an inert electron conductor. So this plays the role, much like platinum does, is our terminal, where it's not actually involved in the chemical reaction. It's just kind of helping electrons move from one species to another. Platinum's way more expensive than graphite, so they're not going to put platinum in these batteries, right? But anyways, same role. It's just kind of helping transfer electrons to what's actually the important part here, which is this material that surrounds that graphite rod, which is this magnesium oxide paste. All right, so it's really magnesium oxide, not the graphite, that's going to be involved in this chemical reaction. Then you have a layer of ammonium chloride, and this is playing the role of your salt bridge. This is here to make sure that your charges stay balanced as your battery runs. All right, and then lastly, we have this zinc canister here, which importantly includes the bottom of this as well, right? The bottom of your battery as well. All right, so let's take a look at our reactions that are taking place for this battery here. Okay, so we have our zinc solid. This is reacting with 2 hydroxide ions. So dry cell batteries are an example of basic condition batteries. This forms zinc hydroxide. Okay, and you can convince yourself because zinc goes from being a neutral metal to having this positive 2 charge over here. We also need 2 electrons to balance out this half reaction. All right, on the other end, we have 2 of those manganese oxides, manganese 4 oxide if we're being good. Reacting with 2 water molecules and 2 electrons. All right, this forms this kind of weird manganese, oxygen, and hydroxide ion. So there's both an oxide and a hydroxide ion here. Sorry, we actually get 2 of those. Let me balance this correctly. As well as 2 hydroxide ions. All right, so given these 2 half reactions, I want you to do 2 things for me. One, I want you to sum these up and give me the overall chemical reaction that's taking place in a dry cell battery. All right, and then I want you to label which reaction is taking place at the anode and which reaction is taking place at the cathode. All right, so importantly, when we sum this up, we're going to see that both our electrons cancel out, which is great, but also those hydroxide ions cancel out. All right, so what we're left with is this overall balanced chemical equation. All right, and then we had these very electrochemistry specific words, anode and cathode. So first of all, let's remember here, which one of our half reactions, oxidation or reduction, takes place at the anode? Oxidation. And reduction is what's taking place at the cathode. We had this really cheesy way to remember this because anode and oxidation both start with vowels, whereas cathode and reduction both start with consonants. All right, and then we want to remember which one is which. Oxidation is what? Losing electrons or gaining electrons? Losing electrons. Remember we had that oil rig. What are those? Not analogy. What are they called? It starts with an A. Acronym. There it is. Oxidation, we're going to lose electrons. Cathode, we're going to gain electrons. So let me get rid of my little red markings here so we can see a little bit more clearly. All right, which one of these half reactions represents losing of electrons? The top one or the bottom one, the zinc or the manganese oxide? The zinc. So this would be the one that takes place at my anode. My cathode would be that manganese oxide reaction. So then in our battery here, right, if this bottom plate is our cathode, oh, nope, sorry. The bottom plate is the zinc. That's our anode. And that manganese oxide, with the help of that graphite rod, is our cathode. Which direction are these electrons flowing, from the zinc to the manganese oxide or the other way? From anode to cathode, right? It's kind of this little phrase that I still have stuck in my mind from when I was in general chemistry. From anode to cathode. This, the MnO2,
Yeah.
would be technically manganese 4 oxide. I've been being lazy by just calling it manganese oxide.
But they're not separated by space. Like it's not like they're at two separate ends of the battery.
They are physically separated. They are not touching one another because of this paste that sits in the middle. There is, maybe this image isn't great. They're not really touching here either. Otherwise, the reaction would happen within the battery rather than conducting electrons around on the outside. Yeah, right? This reaction will not occur unless you stick a wire that connects those two ends together. That's what's going to allow the reaction to occur. Otherwise, we couldn't store these batteries. The reaction would happen, and then they'd be worthless to us. So no, these chambers are physically separated. In this case, it's a paste that separates them, so that's a little weird. But yes, they are separated from one another. So the reaction will only occur when you connect the two ends together. And that's why we love these batteries, honestly, is because they sit and store for a very long time compared to, some other ones.
Wait. Okay, so it's just the diagram that's off then?
I mean, this little bit right here, I think, is trying to illustrate that this must be some non-conducting piece that's preventing these two ends here. But no, your negative end, the zinc here, is not in contact with that manganese oxide paste. Otherwise, it wouldn't be a battery. You'd just have a redox reaction taking place.
Right, so how does the wire connect to both of them? Like the wire that's in the middle, how is it connected to both?
So the wire's on the outside. When you stick this thing into, say, your remote control, what you do is connect one end to the other with whatever's being powered in the middle, your remote control. So it's a wire. You could also drain a battery by just...
Two ends of, like, when you put a battery in, it has these two ends.
Exactly. Right? So and the electrons are then going from there through around into the remote control and then back to the other end of the battery. Okay, so another one that we're going to take a look at, another common one, is what's called a lead acid battery. Otherwise known as a car battery. All right, unlike our dry cell battery, these are considered to be wet cell batteries because you have your cathode and anode literally submerged in an aqueous solution that's a mixture of sulfuric acid and water. So I think we've all heard of battery acid, right? That's where that term comes from, because these two plates are literally sitting, these two terminals are literally sitting in this acidic solution here. All right, that acidic solution is what's playing the role of our salt bridge. It's going to help maintain that ion concentration. Okay. Car batteries, if you've ever had to deal with them, you got to dispose of them in a specific way. You can't just throw them into the trash can, because a trash compactor will smush them and spray acid everywhere, right? So you're supposed to like take them to the dump, and you got to do something special with them. Anyways, all that to say, because there's literally just a solution of strong sulfuric acid in the middle of that battery. And what we have here, it's a little bit complicated, but what we have here are alternating plates. In blue and in red here are our alternating anode and cathode plates. All right, within a battery, they're actually separated into these 6 chambers. Each is about 2 volts. All right, so together that makes that car battery about 12 volts. This is now getting into a little bit of circuit talk, which is more of a physics sort of thing. But nonetheless, we can just note that they're fairly strong batteries. I guess just for comparison, your AAA, AA batteries tend to be about 1.5 volts. All right, so a car battery is meant to be quite a bit stronger. Okay, so again, let's just take a look at our half reactions here. One of them, it's called a lead acid battery, because lead's an important component of both. One is going to involve lead oxide, and the other one what they call spongy lead, which is just kind of a porous solid lead. All right, so let's do our same game here. Let's look at these half reactions. All right, so that lead oxide reacts with that sulfuric acid and 3 protons, as well as 2 electrons. So it starts as lead 4 oxide and then becomes lead 8 oxide. And 2 waters. This will be good. All right, and at the other end, we got that spongy lead reacting again with this hydrogen sulfate from our sulfuric acid to produce lead sulfate, a proton, and 2 electrons. All right, so let's play this same game here. I want you to tell me what the overall reaction is for this battery, as well as label your anode and your cathode based on these half reactions here. Yeah, you got a good point. I don't know. This is just what I grabbed from the textbook, so we're going to roll with it. It's true. We do have, it's actually this side over here that we're missing something. Maybe there's a sulfate ion over here produced. Let's see. See if we can figure it out real quick. No, I don't know where that would come from. Yeah, there is something wrong with this one, but whatever. We're going to roll with it. This is more for fun anyway. We don't have to have these memorized or anything like that. All right. Importantly, and this is like kind of the most important thing that I want to make sure that we can do here, is make sure that we can figure out what's being oxidized, what's being reduced, and thus what must be our anode and what must be our cathode. All right, so our anode here would be that spongy lead. This is the reaction, oops. I'm sorry. For y'all here, which reaction is going to be our oxidation reaction? The top reaction or the bottom reaction? So we're losing electrons if they're on the product side here. So this is our oxidation reaction, which implies this is our anode. So that spongy lead is the anode of our battery. And our reduction reaction taking place at that cathode. All right, but this battery here kind of leads us into our last topic for our discussion here today, which is these car batteries, while they do pack a big punch in terms of their voltage, they tend to die pretty quickly because in both of these half reactions, you produce these solids that end up building onto those terminals and eventually kind of clogging them up so they don't work anymore. All right, so what you may or may not realize is that your car battery is really only important for the very beginning of your journey when you start your car. Right? That's what your battery is actually used for. Once the car's started, the battery doesn't get used anymore. Your engine takes over and provides the electricity to the rest of the car, and importantly, charges that battery back up. You have a component of your car called an alternator, which is where the engine's energy is being used to recharge this battery. Okay? So if this battery is running the way that it should, that means it's going in this reaction is going in the forward direction. If we recharge a battery, what does that mean in terms of the direction of our reaction? We need to drive everything in the reverse direction. All right, so how the heck do we go about doing that? Okay, so we can recharge a battery as well as a process, all right, or rather this is closely related to a process called electrolysis. All right, so when a battery works, what you're saying is that the potential of that battery is greater than 0, meaning the reaction runs spontaneously in that forward direction. As we said, to recharge a battery, we need to then drive that reaction in the reverse direction. Well, if it's spontaneous in the forward direction, what does that mean about the reverse direction? It's non-spontaneous. So that means that we have to drive a non-spontaneous reaction. right? If it's spontaneous in the forward direction, that means it's non-spontaneous in the reverse direction, and that's the direction we got to get this thing to go in. All right, so how do we do that? That is what we call electrolysis. Electrolysis is when we use electricity to drive a non-spontaneous reaction. And we're going to see it applies to recharging batteries as well as other cool redox reactions as well. We can get an unfavorable reaction to happen by providing an external power source, by providing electricity to drive that non-spontaneous reaction. Okay, so first, let's go back and look at, we got this diagram. This is of our normal old, what's called a either galvanic or what we called voltaic cell. Those are synonymous with one another. All right, and importantly, this is whenever you have a voltaic or a galvanic cell, again, synonyms, this is a battery that's driven by a spontaneous redox reaction. All right, so in this example here, we have this cadmium copper battery here. All right, I want everybody to take a second. You don't have to sketch this whole thing out, but let's go ahead and copy down our two half reactions here.
You said it's driven by spontaneous.
It's driven by a spontaneous redox reaction. That's what like these batteries that we've been discussing thus far. All right, so just given these two half reactions, I want you to tell me what the anode and the cathode is, as well as label your positive and negative terminal. All right, so which one's our anode? The cadmium setup or the copper setup?
Cadmium.
The cadmium setups are anode, coppers are cathode. So then which one's positive? Anode or cathode? All right, our cathode, because that's the direction that our electrons are drawn towards, is that positive end of our battery. Okay, so we have this cadmium anode and this copper cathode. Let's go to our constants page here. So first of all, I guess let's just look. This thing is hooked up to what's called a voltmeter, which drives me nuts. I feel like voltometer was right there and they went with voltmeter, but okay, whatever. Anyways, this is what you use to measure voltage. So if we stuck this little voltmeter in the middle here, what voltage would we expect to measure? Everybody take a second. Given our half reactions here, tell me what the potential of this battery is. All right, so remember, we're going to take our potential at our cathode and subtract the potential at our anode. So when we hook this up to our device here, we would expect to get a voltage of 0.74 volts. All right, so again, this is our voltaic cell here, our normal battery. This reaction is being driven by this spontaneous redox reaction where cadmium is losing electrons and copper is gaining those electrons. All right, now we're going to go over to this one here on the other side. This is a very similar setup, but this is what's called an electrolytic cell. So this electrolytic cell is now going to be driven by this external power supply. All right, so what I did was I took out my voltmeter and I put in this new device here. And this is actually connected all the way to the plug in the wall here. I'm supplying some external power source to this. All right, and the reason why I hooked it up to this external power source is because now this external power source is going to drive electrons in the other direction. All right, so driven by an external power supply in the opposite direction. All right, so in my normal old battery, we said that our copper was being reduced and our cadmium was being oxidized. Well, if we look carefully, now that we're driving electrons in the reverse direction, what's happening to our copper and our cadmium? Switching roles, right? So now it's my copper that's being oxidized and my cadmium that's getting reduced. We're still going to keep this same terminology with what's being reduced is the cathode and what's being oxidized is the anode. All right, so now we can just note now copper is oxidized, cadmium is reduced. All right, again, we're still going to say that our anode is where the oxidation occurs, and the cathode is where the reduction occurs. All right, but if we think about it here, in order to drive this reaction, we're going to have connected that anode, our copper, to the positive end of our power source. Because electrons are flowing in this direction now. Let's see if I can use a better color. There we go. All right, so now our cathode, or rather our anode, is connected to the positive end of this power source, and our cathode is connected to the negative end of this power source. So our signs have flipped here. Now my anode is considered to be the positive end of this electrolytic cell, and my cathode is considered to be the negative end of this electrolytic cell. They don't stay the same side.
So yeah, we switched.
We did switch.
Okay.
What does remain the same is we say oxidation anode, reduction cathode.
Okay.
Right? It's just now we've switched what's being oxidized and what's being reduced, and we've switched the direction of the electricity, so we got to note our sign change as well.
So the thing that does never change is that positive is where electrons are going to.
Correct.
And negative is where they're coming from.
Correct. That is always true as well. Yeah. And yeah, I guess let's make this even more clear here. Why do we call it the positive end? All right, because it's connected to the positive end of that external power supply. And why do we say that this is the negative end? Because it's connected to the negative end of that external power supply. And yes, electrons will always flow from the negative to the positive end.
So when you say down here with what you've written, when you say the anode is with oxidation is positive, is that in terms of the original? Like if we're looking
Well,
at
no. So if we went over here, anode would be where oxidation takes place. And that's what we called the negative end of our normal voltaic cell. And over here with our voltaic cell, our cathode is where reduction took place.
yeah,
But that was the positive end of our battery.
right. So why does it switch? Like just because we have that outside power source?
Correct,
So-
because that is what's driving the electrons. So the electrons are not being driven away by the copper. They're being driven by the external power supply.
Because the metal pieces keep their charges as negative and positive charges. Like I was looking for the one thing that didn't change, basically. And so that piece of metal has like the cadmium or whatever has that negative charge on it.
But it's not a negative charge. It's the direction that the electrons are flowing from your power source. They're moving away from the negative end of the power source. Whereas here they're moving away from the negative end, but they're being driven by that cadmium there. They're being released from the cadmium. Here they're being released from the external power source.
We could define it in a way that keeps it constant, where the cathode is the one that gets reduced spontaneously. So even though this part is being oxidized in this example, it's not being oxidized spontaneously. It's being done to it.
Right.
But it stays
Which
the
I'm
cathode
following,
because
but I don't know. I think
Oh.
I missed something that he said, and I think that it's fine.
So I think the important part is to realize where the electrons are being originated from, which is this thing in the middle, right?
Yeah.
So there's a negative end of this. It's almost like there's a battery in the middle here that's driving everything, not our reactions. So the external power supply is what's releasing electrons from this end here, and then they're traveling through to this end here.
Okay.
Oh, they did switch names. Okay. Copper is the anode.
Yes, the copper is the anode because now the copper is being oxidized.
Right.
Yeah, so what didn't change, if we just want to play the spot the difference game, anodes being oxidized, cathodes being reduced, cathodes being reduced. Our charge sign here, our positive and negative, is what changes. Now our anode is not the negative end, but the positive end. We call it the positive end because it's connected to the positive end of the external power supply. What's up?
But the charge doesn't change for the not reaction, but the section, the half reaction though, right?
The half reactions did change, yes. If we look here at our half reactions, just to kind of show, by using this external power supply, our copper is no longer being reduced, it's being oxidized.
But it's still positive for both.
What do you mean positive for both?
Did I just write something down wrong, or I was just
The copper is still the positive end of the battery?
yeah?
Yes.
Okay, so that doesn't change.
No. Importantly, though, because in our voltaic cell, it's because that's where the electrons were being attracted to, whereas in our galvanic cell, They're being driven by this external power supply, which is where the electrons are being attracted to. So it's no longer copper that's doing the driving. Copper's not in the driver's seat anymore. It's this box in the middle here that's connected to the external power supply, right? And that external power supply is pumping electrons in the opposite direction.
Right. Oh, because we're talking in the terms of recharging, right?
Correct.
So, okay, so instead of those two things powering the thing in the middle, they are being powered by the thing in the middle.
Exactly.
That makes way more sense.
Yes, correct, right? We're no longer just measuring. This is the voltmeter is a very passive thing that's just measuring what's going on. This thing is now actually doing some work and pumping the electrons in the opposite direction, all right? Not only that, but let's think about it. If this thing wasn't here, the reaction would be going in that other direction with this potential of 0.74 volts. So how strong is our external power supply going to have to work in order to actually drive things in the other direction? It's going to have to be greater than 74 volts.
Can volts be negative?
Volts can be negative, but that just means that you're going in the wrong direction. So you would have it would drive at 0.74, greater than 0.74 volts in this direction here. Cool. So the only way that you could recharge a battery is with a stronger battery or an external power supply. I mean, basically buildings like this, an outlet has a potential of 110 volts, right? And that is just this potential difference from one side of the building to the other. We take advantage of that, plugging stuff into it, right? But yes, so you could use something that's greater in voltage in order to drive the reaction in the other direction, okay? So that goes for recharging batteries. We could also just take a look at a non-spontaneous redox reaction. All right, so let's try to drive a non-spontaneous redox reaction. All right, and we're going to look at one that's actually used quite a lot industrially, and that is to take sodium chloride and decompose it into its two components, sodium metal and chlorine gas. All right, both sodium metal and chlorine gas are highly reactive, so they're used for industrial purposes. You don't really find them out in nature in their pure form because they're so reactive that as soon as they get together, they'll go in this other direction, right? So this reaction right here is the one that we're going to try to drive. Let's convince ourselves that this is indeed a non-spontaneous reaction. What would we calculate for this? Our delta G. So let's look up and calculate our delta G naught for this reaction. We got to go back to our thermodynamic standards constants page. All right, so let me grab these values real quick. Oops. That did not work. Here we go. Just going to save myself some time, grab this whole block. Cool. And which column were our delta G's? Does anybody remember? The middle column. right, so remember it's products minus reactants. So 2 times 0 plus 0 minus 2 times negative 384.1, or we get a delta G of positive 768.2 kilojoules per mole. And so based on this value, we would say, what about this reaction? It is very non-spontaneous. Which is great, because that means we're not worried about our sodium chloride in our kitchen cupboards spontaneously decomposing into toxic chlorine gas. This reaction really does not want to go in this forward direction here. But that's what we want to do, is we want to drive it in this forward direction here. All right? So how are we going to go about doing that? Well, let's use our relationship between delta G and our E naught. First, we're going to need to look at our half reactions. All right, so we're going to have to break this up into our 2 sodium ions. Becoming neutral sodium, and our 2 chloride ions becoming neutral sodium, I need 2 of them, becoming its neutral diatomic chlorine gas. All right, if we're going to charge balance these half reactions, everybody take a second, tell me what's being oxidized and what's being reduced by charge balancing these half reactions. All right, so we need our chlorides rather, to be oxidized and to reduce those 2 sodium ions. And again, this is the exact opposite of what these things want to do. Sodium wants to lose electrons, chlorine wants to gain electrons. So again, these are non-spontaneous. All right, but now let's use our relationship between delta G and that E naught. All right, and specifically we want to solve for that E naught, because now we have our delta G naught from our table. All right, so I'm going to be good about my units here to make a point. I'm going to plug this into my calculator. I get negative 0.00398. Right, and so if we look at our units carefully, we'll see that everything cancels out except for kilojoules per coulomb. But that's not what a volt is, so now I'm going to have to do a unit conversion here so that I can get to joules per coulomb by multiplying by 1,000. So we get negative 3.98 volts. Again, based on the sign of this potential, we can again conclude exactly what we knew from our delta G, that this is a non-spontaneous redox reaction. All right, but now we want to ask how much external power will we have to supply? All right, well, in order to overcome this potential right here, that external power is going to have to be greater than -1 times that potential of our standard potential of our cell. All right, so in order to get sodium chloride to decompose into sodium and chlorine gas, we're going to have to supply an external power of at least 3.98 volts.
So
Okay.
I'm not a terrorist or anything, but I could like decompose salt just by running a current through it.
Yeah.
It would just.
Yeah, you look it up on YouTube. It's like more efficient. They heat up the salt so it actually turns into a liquid. It seems to like it's a molten salt electrolysis is what they call it. But yes, you can absolutely decompose salt by running a current through it. Now, practically speaking, if you only ran 4 volts through it, I don't know if you'd have to wait a million years. I think maybe they probably crank it up to get it to occur on a reasonable time scale. But again, the outlets are 110, so yeah, you could do it pretty easily, right? But yes, absolutely. You can see people do it in the lab as well. So yeah, if you look it up on YouTube, you can definitely find them decomposing molten salt. They do this process industrially quite a bit because especially chlorine gas is a really useful starting process in synthesis reactions. You can also do the electrolysis of water and create pure oxygen gas and pure nitrogen gas. You can drive non-spontaneous reactions by applying an external power source. And how much power do you have to apply? Well, it's based on the delta G of that reaction. You need to overcome this much energy in order to get the reaction to go in that direction that it really doesn't want to, right? And so that's what this calculation here is showing, using our relationship between delta G and our potential of our battery. We get an idea of just how much power has to be supplied in order to drive this non-spontaneous reaction.
We would have to adjust it for the standard conditions though, right? Because this is in standard conditions.
This is in standard conditions, although we have a solid here, so we're not going to be too concerned about our conditions of how much of this we start with, for example. This process would be independent. Now, as we start to build chlorine gas in that system, that might be a problem. But that's kind of easy enough to siphon off as it's being produced.
Oh.
But yes, this is strictly speaking for our standard conditions here, based on that standard potential and that delta G of our reaction, delta G naught of our reaction. Cool. All right. So that does it for our discussion of electrochemistry and batteries. We're going to take our break and then we'll get started on our lab report for that solutions and thermodynamics lab.
Professor,
What's up?
is this section related to? I just saw like a video where like a girl had put something that was battery powered into water and wasn't cutting off, and someone was like, "Oh, put salt in it." Is that related to this or?
Kind of. So basically, water is not a good conductor of electricity unless there are ions in it, and then it becomes a better conductor of electricity.
So will dissolve into ions.
Correct. Yeah.
It'll just take on that electrical.
Electricity has an easier time passing through it if there are ions floating around in it. That's where that term electrolyte comes from, which is just what like an electrolyte solution or just ions dissolved in water. They're called like that term comes from the fact that they realized, oh, if we dissolve salt in water, it conducts electricity better.
Okay.
You kind of just give a path for those electrons to go.
So it like overpowers the electric current and then just like kills it? Or the battery, I guess?
I don't know the exact example that you're referring
I'll
to,
have to find
but
it. It was pretty